guys are here on time, so thank you very much. And we'll just let everybody trickle in. I really appreciate you being here, and I very much appreciate the guidance of Jim Brodnick, who is from Lockheed Martin. And Jim also sponsors the UME competitions. He's been the tournament director, I guess is your title. Tournament god. Let's just make it really big. And sure. He's worked with a lot of teams. He's the expert. And when he kind of introduced Sugo to me, I thought, well, this is perfect for Stamposium because it's something we don't have to do in a separate gym. We don't have to move giant tables around, and it gets everybody to learn new skills. So this seems to be ideal for me. Now, each one of your teams, as they're entered into Stamposium, will get a field. You've already got your EV3, but you'll get a field that's not as fancy as the one that Jim has built. But what Jim was just telling me is these are actually better because then your robot doesn't fall off and you don't spend so much time rebuilding stuff. But you'll have this issued to you. It's the exact field. So you can practice on this. When we get to Stamposium, then we will be using one of these elevated board things, but trying to source those is impossible. So thanks to Grand Prairie High's building trades class, they're actually making those for me right now. So you'll be issued these after February 3rd, as soon as all of the entrants are finalized, then I'll be issuing these so everybody gets them at the same time. And I'm gonna turn this over to Jim so he can explain to you a lot more about Sugo. Thanks for being here, Jim.
Thank you. Well, again, thank you guys for all coming. We appreciate your time. I appreciate being here, Al. I welcome the opportunity to share about robots. And as I usually say, yes, I have slides. That's really for your benefit because it keeps me on track. Otherwise, we would miss dinner and probably start at school tomorrow. I do like to talk about this stuff. It's just great to see the kids learning and their interest in science, technology, math just really come alive. So what we're going to do today is just going to do a high-level introduction to what Sugo is. Give you some little tips, let you see a couple of robots. So, Chinese sumo wrestler with Lego bricks, you get a Sugo bot. And that's how the whole thing started. What is the Sugo challenge? We're going to use the Lego Mindstorm kits, the EV3. We have an EV3 here to show you. If your school has EV3s, they're perfectly great for that. And the EV3. What happens is you have two robots on the field like you see. The object is to push your opponent out before you get pushed out, just like sumo. So that's the easiest way really to do it. We're going to show you a little bit of action from the 4-H. Sugo originally started, from what I can find, in the Northeast as 4-H projects. And the kids get very loud. We turn the sound off for your benefit. It is a loud tournament, encouraging the cheer. That is great. They help each other out. They learn to build. We use this as an introduction, kind of. We started this program really for 3 reasons. We needed something to do in the spring after our first Lego League had stopped. We needed something to introduce new students to how to build without overtaxing them. Introduce new coaches without overtaxing them. The main reason we started doing this is a lot of our teams would not use sensors. You cannot do this without sensors. The object is to stay on the board. As you can see, that light sensor right there is detecting the black line and keeping the robot from falling off. If you're not using a light sensor, what's going to happen? The ultrasonic can be used to detect your opponent. Now, Sugo actually makes a 3-way infrared sensor. I've seen use in it, but they're expensive and can be done with the ultrasonic as well. So before we go any farther, I'm not real formal on lectures. You can raise your hand, stop me anytime, ask questions. I'm good with that. So, let's see, I don't know how much longer. I think it's just about done. And print things, use them. So the rules are online for the event at the website. If you haven't already got those, there's the address up there. We're going to go over the rules. I find that coaches, as well as students, tend to neglect doing that. You need to know the rules. As any good engineer does right off the start, they need to know their constraints. They need to know what they have to follow. That is really what this is about, teaching good engineering principles to our students. So rule number one, it must fit in a 7 by 7 inch box. And we have one built here. There's a lot of different shapes. You can measure with a ruler. Now I built both of these robots last night by eye. I didn't have my box. And I am close. Okay. So you can see how hard it is to do it. It's a constraint. Every engineering process has constraints as you go on. So that is one constraint that we're working on with the kids, is a size constraint. The other one, well, we're going to get that to number 3. Let's go to number 2 first. It must be made entirely of Lego parts. It's very simple. One thing that I would suggest, though, is to tell your students not to bring their own parts because they have a tendency to get lost and mixed in with yours. So I would just say, no, you're limited to the kit. This one's built, other than the minifig, with everything out of an EV3 core kit.
Other than the what?
The miniature figure?
The minifig.
Oh, okay, all right.
The little man, which really is not important, but he adds some character and we like to do that. And we're going to explain that in a minute too. So that one is entirely made of a core kit, which you guys have. It can be done. The weight limitation is the next one, 26 ounces. I don't know who established that, that's just what it is. So it's 26 ounces. It does become a challenge quite a bit to keep it under 26 ounces. We found that the lithium batteries tend to weigh a little less. The 6 AA's will push you over. And yes, it's with the battery attached in that we want to do this. So that's a constraint that you often work with within engineering. Okay, what's the weight limitation? You're building a vehicle or a military vehicle. You face weight limitations all the time. Keep a bill of materials for the robot. What this is just a list of the parts. And they must be submitted at the time of check-in. The day of the tournament, you will have a check-in. You will have your robot measured in a box. You will check the weight. We usually give kids, depending on how much time you have, 15 minutes to make adjustments. They can be inspected with whatever time limit that you want to set that to. Bill of materials. The easiest way to do this is, in the packets that are online as well, is a core kit. They call it a survey. It's all the parts with a little picture and a part number with it. So what you do is you just take a simple hash mark system. Say I'm using a 15M beam, which is the longest beam available. You just mark it. You mark it, and then right before the tournament, do it in pencil because you will make changes. The students will make changes. Then at the end of the, right before the tournament, you want to take and total it up. Say, part number so-and-so for the beam, I've used 5 of them. And that's what you would turn in. At the end of the presentation, I have some online references that if there's a part that's not on that list that you have, that they can look up and get the part number for. We've also talked about possibly having to do a cost associated with that, but I wouldn't start off with that and set a cost limitation. That would be a little more advanced. A maximum of 2 motors are permitted for movement. So you have 2 drive motors on this, as you can see here. You are allowed a 3rd motor for any attachments. I've seen some very creative ones where they put arms that try to sweep the other robot out of the way. Arms for trying to lift the robot up like a sumo wrestler would. A little more complex. If your kids have time, encourage them to try it. The robot cannot have any device that obstructs the control of the opponent, such as a jamming device or a strobe. You're using the ultrasonic. You don't want any jamming devices. I think we have a tolerance on it too. The robot will not include any part that can damage or deface the field or anyone. You always get the question, can I use a saw? No. You cannot attach a saw to your robot. Can I make it split fire? Well, if they could, you know, it's still not a good idea. You don't want to ruin the kids. I'm sure Miss McGee would be very upset if our kids came back melted. So the idea is anything that would damage the opponent's robot or the field, not permitted. A robot will not use any part that fixes the robot to the playing field. They can't come up with some kind of suction cup or anything that glues it to the field. Not legal. The robot may start in any position on its side of the ring, as you saw when she held up the ring. There's 2 gray lines there. You can start, and it always becomes a thing of contention with the kids, I guess you could say, because they learn that, hey, if you start this way, that robot charges straight, so they'll want to start it. And they want to move the robot all the time right before they start. So what we do is, robot's down, once you give the thumbs up, you're ready to go, you cannot move the robot anymore. Otherwise, they're jockeying back and forth. So he moves his robot over here, and this team would move it over there. And it was going on forever. So, and Mrs. Milam is one of my coaches in the back of the room back here. This is actually going for a demonstration tomorrow morning or next morning. So she's here to pick it up after we're done. She can tell you how true that is.
Oh, yes. You're counting down as there's 3, 2, 1.
So, to eliminate some of the contention, it's to say no. Put it down, it's set, thumbs up, and it's set in place there. The robot must wait at least 5 seconds, and we'll look at the program and show you how to do that at the end here coming up before you start. The reason for that is ultrasonic sensor. If my ultrasonic sensor is facing this way, and it's reading 12 inches out, and I'm still standing there, what's going to happen? It's going to read positive and try to advance towards me. So the 5-second delay is to push the button and have the students move back at least 2 feet. That way there's no interference from surrounding people, plus that also lets other people see much better. It must be autonomous, all actions must be pre-programmed. No method of remote control. Are you all familiar with the Lego Mindstorms to a degree? They can be controlled through Bluetooth. We make the people disable the Bluetooth. Bluetooth is a wonderful thing, especially on the EV3s, because you get real-time feedback from the sensors. It's a great troubleshooting tool. So if you're connected to your EV3 by Bluetooth, you can pull up the program, go to the sensor mode, and actually see what those programs are doing. And we may do that if you guys have time and would like to see that for other reasons. Robot design. So what we're going to cover now is a little bit about the engineering design process, some tips and tricks, and I've kept these slides to a minimum so you can ask questions. So please do, we're going to be done really quick. This is a very basic engineering design process. I think it works well for the 4th through 8th grade. We started off with a NASA one, which was about, I think, 10 steps. It just didn't work well. So this is a little more simplified. It's a common one. It's on the web, available in many different things. So you start by asking, what is my design supposed to do? Then you imagine, apply knowledge and creativity to brainstorm ideas. Okay, how can I make that robot accomplish what my task is? Then you plan ideas with sketches, drawings, notes. Have any of you seen the Lego Digital Designer? It's a generic CAD. It's on the reference page. I'll give that to you at the end. It is a generic CAD by Lego that all blocks are pre-programmed. So you can kind of start just by dragging parts in and building robots. It's great to do. It's not the best, especially if you tell it to build the instructions to build the robot you drew, because a lot of times it has parts just floating in there. Put this part here. Okay, there's nothing to attach it to. But it's a great idea to see how parts interact. You can actually do some rotation on the parts, make parts move. Okay? So it's a nice little program. Then you create a prototype. That's the next step. Okay, I built what I've talked about. Then you test it, and you improve it, and the whole circle starts again. You ask, what can I do to improve my design? Can anything be made more efficient? And that's kind of where we're going at next with these. Well, let's set a couple slides down. Common attributes of the Sugo robots. 2 motors are used for drive wheels. Okay, we don't have a steering wheel on these, correct? So how do you steer? Just like a tank would. And we're going to talk about turns in a minute. So by turning one wheel at a different speed than the other is how you get the robot to turn. And I'm going to show you the 3 types of turns that are typically used. We'll demonstrate a couple of them on these robots. An optional third motor, as we talked about, can be used for any type of power attachment that they want to do. Color sensors for detecting the edge of the ring. It's very easy to detect black from white. It's not a hard program. We'll point you to some programs to show you how to do that. Ultrasonic for detecting the opponent. Touch sensors. Neither of these two employ a touch sensor. But it's very easy to use a touch sensor, so if it makes contact with your opponent, that you change something, maybe increase the power of the motors, for example. So there's a lot of different things, or maybe it activates the lifting device that your student built with a third motor, or these, we're going to call it a slap arm for lack of a better term, the arm that would come across and push the robot from side to side. So there's a lot of different things you can do with a touch sensor. Now we're going to get into the chassis durability. These are just questions that you can use to get your students to be thinking about durability. Does my robot stay together during routine handling? If I pick my robot up and it falls apart, how well do you think it's going to do on a Sugo field when it's getting pushed around? Probably not real well. Does my robot have excessive flex when moving? Does it give and bend and twist? So as I said earlier, the great thing about Legos is they come apart. You can build many, many things with them. The bad thing about Legos is they come apart, usually when you don't want them. So if you got a lot of flex, that usually will accelerate your robot falling apart. So you want to keep an eye on that.
Can I glue my parts together?
No. That was Mr. Business from the Lego movie, right? No Craggle here. Okay?
The kids will try.
Yes, you'll get that too. Can I glue the parts? No. Yes, sir?
Can we unglue and then craggle it?
No. No Craggle, no glue, no tape. That's the nature of Legos. Does my robot wheels remain in contact with the field? One of the biggest things in this competition is traction. You will see as these robots start to go that the wheels will start to slip. I've intentionally used 2 different types of wheels, so that I'll kind of explain why I did that a little bit later. And as you can see on this one, I've actually doubled the wheels. I'll give you one guess why. Traction. Okay, this is an old style wheel. Oh, probably 10, 15 years old, but it still has some great use. Mechanical efficiency. Why do we want to be efficient with these robots? We got a guy that's really interested in it. Tell me, sir, what's up?
So like we don't want them to actually like deactivate or something's wrong during the battle.
That's right. We want it to be reliable, but we also have to remember we have constraints, right? We have a size constraint. If we're not efficient with our parts, what's going to happen to our size? Typically, it's going to expand. We have a weight limitation. If you're not efficient with your parts you're using, what's going to happen to the weight of the robot? It'll typically rise. So efficiency in parts is a good thing to have. In most engineering processes, you don't want a lot of extra parts. A lot of extra parts usually has a side effect of something going wrong. The more parts and more moving parts you have, the more chance it has to fail, right? That's common sense. So you want to be efficient. So things we can ask about that. Number 1, these things run on batteries, right? What happens to batteries? They die. You have to recharge them. Can I get to my charging port easily? Okay. If I can't, I have to take the robot apart to charge it. Now in this case, this is the AA batteries. I have to physically take the brick off to change the batteries. Can I do that easily? These are questions you want asked. Batteries do die. You need to think about that. Can I see the display? You'll see a lot of kids start building things over display. What happens when you're trying to navigate the program if you can't see the display? Makes it hard. Can I plug and unplug wires easily? If I have to take it apart and I have to unplug the wires, can I get to them easily? I'll stop there to add this in. What do you notice about these two robots? Are there a lot of cables hanging off of them? Why do you think I did it that way?
No snag on anything?
Yeah, they get snagged. I left these ones loose in the back for a reason, and I'm hoping it does it. I've seen many robots get caught by their cables and dragged off the field. So, it's a good idea not to tuck them in a little bit, like this one here. What are the chances of this robot getting caught by its cables? Very slim. It's not hard to do, it just takes a little bit of thought as you're designing. Are the wires in the way? And how long does it take to set up my robot? If you're trying to get to it and playing with the buttons because you can't see the screen, it's frustrating. Right? This robot here caused me a lot of problems last night. And the only way I could resolve the program, I'm going to turn them on now so they can start to power up. May take a second. The issue I kept having with this robot last night is I wanted to run it to charge my opponent at 100% speed. The problem was it never stopped fast enough when it hit the black line and just kept on going off the board. So that's what we mean by appropriate speed. You may want to run everything at 100%. Most students do. 100%. Let's do it full out. That's not always the best idea. Does your robot have the right wheels? Bigger wheels, larger circumference, move faster. One rotation covers more distance. Basic math, right? Smaller wheels or wider wheels actually provide more traction, more friction, traction. That's why I doubled these, because the narrow wheel, yes, this robot's fast. The original intention is why I put the big wheels on this was to gear the wheels down. So if I gear them down, so it runs slower naturally, right? My motor tones maybe 4 or 5 times to get one rotation of the wheel. So I was going to counter that by using a larger wheel, get more torque, and I didn't get that far. The night was way too short. So those are some things that you can remind your students of when they go. Center of gravity. Any experts here on the center of gravity? What happens, a few years back now, a number of years back, there was a lot of talk about SUVs and being rolled over. Why was that?
Your top end.
Top heavy, center of gravity was high. If your object is to avoid getting pushed out of the ring or toppled over, would you want a high center of gravity? Okay, both of these have pretty high center of gravities. The one, and I couldn't find a picture of it, I actually dropped the brick down below the motors. You got the heaviest thing on here is your brick, which is the control unit. So that gives you an idea of some of the things you can do to help improve that. I think this one may have a little issue with the center of gravity too. I think maybe a little front heavy. So when I get close to the end of the board, it's pulling it down as well. So center of gravity, both vertically and horizontally, can affect your ability to do well in these competitions. Where gears help, I kind of explained to you what I was looking to do with gears. Gears can help. Little gear on the motor, big gear on the wheels, increases the torque, slows the robot down. The opposite will give you great speed, less torque. So that's something you can work with. We give a reference at the end to a very good site on Lego gears. Here, it can kind of help your students understand how gears work and what Lego gears work well together. Considerations of the chassis. Remember, you have to fit in the box. I keep saying that because it is a challenge. A bigger chassis requires more power, draining the batteries quicker. These are DC motors. Not that it should be a problem in the tournament, but it's just something to keep in mind. More weight, DC motors require more power to move it. Remember, after the robot, you'll need to get to the batteries. We talked about that. Wires from the bricks should be tucked away so they don't get caught. Let's see. Types of chassis. I've seen a couple 6 wheels robots. I built one, tucked it all up underneath. I put wheels on each side of the motor. As you know, motor is 2-sided here. And it did fairly well. I think that was last year's. We call him Willie for a good reason. We'll talk about naming the robots here. Treads. Students love to use treads. Treads are more difficult to control the turns on, and they don't seem to have a whole lot of traction at times, especially on these fields. If they want to use them, let them, encourage them. Try to show them, hey, this is the difference. If they insist on doing it, let them do it. This is about learning. Don't be afraid to let your students make a mistake. And then help them understand what they can do to improve it. That is the learning process. We really need to get back to letting students make mistakes and be there to help them recover from them. That's enough of my lecturing on mistakes. Wheels. You can have, both of these robots are using a method of this. This one has a caster up front and the 2 wheels. This one has the EV3 rollerball caster and the 2 wheels up front opposite. Did that just so you can see the difference. Tracks, we talked about low friction and high slippage in the wheels. Wheel support. The nice little thin axles we get with Legos, you ever notice how flexible they are? There's multiple ways that you can actually help improve that. We actually have supported on both sides with this robot. And you're welcome to come up and look at these robots. We're going to run them a few times. I think we got 2 volunteers to push the buttons, right? Or maybe 3 now. Yeah, cool. This one uses supports on both sides. That's what these outer rails are for. Plus, that helps protect the wheels from the other robot. This one is using more of a direct drive. And if you look, I have a beam that's actually tied into the wheels, which interlock with the Lego wheels. How many of you knew that the Lego wheels have those holes in it for a reason? You can attach beams to them. And this outer wheel is actually held on nothing. Gonna pull it apart. It's so tight I don't even know. With beams. That's the only thing that's holding it together. That beam provides a lot more support than, now watch me not be able to get it back together. A lot more support than just that thin little cross axle you have. This works great in FLL too, coaches. Helps the accuracy. 3 types of turns. When one wheel moves at a different speed from the other. The greater the difference in the speed, the faster the turn. These robots typically have 3 types of turns that we discuss: a pinpoint, a pivot, and a curve. So, we're just going to do a quick diagram to show you how these work. So if I brake the right wheel here and apply power to my left wheel, that robot is going to go right, correct? If I reverse it, what's going to happen? It goes the opposite way. The easiest way to think about this is like a basketball player. You can tell your kids, hey, you plant 1 foot and you pivot. That's why we call this a pivot turn. That's the easiest way to explain this to them, is a pivot turn. Brake 1 wheel, yes, you should brake it. That means you actually physically apply the brake into programming to that wheel. It holds it much steadier than just leaving it loose. A pinpoint turn. Any questions on the pivot turn? Pinpoint turn is the wheels rotating the same speed in opposite directions. That'll rotate, I think this one's using the pinpoint turn. If you do that, the center dot in there is what the robot rotates around. It's a much tighter turn than a pivot turn. Then, if you rotate the wheels in slightly different speeds, you have one going slower and one going greater, it's an arc, much longer curved turn. Do all you guys do FLL? All of you? There was a great place to use a curved turn this year on the field. So anyone want to guess where that was at? Not the Panda. Go ahead.
Milking station?
Milking station was one of them.
We need to make the dog.
Okay, the blind man crossing and the knocking down the fence, that's an ideal curved turn. It can be done if you mess with the speeds on the wheel a little bit, some fine tuning and adjustment. That is nothing more than a curved turn. Consistent steering. I should have brought the other wheels. The other robot too. Have you ever tried to steer one of the robot with four wheels with the actual tires on it? It doesn't work. The friction is so bad. In the chassis demonstration, we actually do that. We have a robot with all four wheels on. We show you each of the turns with the wheels on, the non-powered wheels on, and the non-powered wheels off. World difference. The friction is just tremendous and keeps the turn completely unpredictable. So before the caster balls came out with EV3 kits, you did one of two things. You used a little skid type wheel or a side wheel, or you just took the wheels off the rim and let them slide there, reducing your friction quite a bit. This is Groucho. He was a few years ago, and we're almost to the end. Anyone want to guess why we called him Groucho?
He's very angry.
No. There was a very famous actor who had big eyebrows, and you can see this robot has eyebrows. Okay, so this was Groucho, and that's one of that. You can see I inverted the motors, and the brick is down pretty low. Really, to get the kids involved, naming your robots, giving them some personality is just a great thing to do. I have these two. I decided to name this one Jester. I have my little minifig on it. You can if you want. You don't have to use a minifig. It's my little Jester fig with his lightsaber. All Jesters need a lightsaber, right? And this one is Dozer for obvious reasons, because he looks kind of like a bulldozer. And it has my construction worker drinking his coffee. So this makes it fun. Have them name. I would suggest you have to approve the names so you don't end up with some names that aren't quite appropriate for school. If all else fails, call it Bob. It always works. But let them choose their names and let them kind of get the personalities of it. So, okay, programming. Any questions so far? You guys must have had a hard day at school. Comment your programs. Okay? The robot will be pre-programmed with a Mindstorm program. A typical program will use the color sensors we talked about, the ultrasonic, the touch sensor, and it had the 5-second delay. Why we mean pre-programmed is you can't remote control. That's the rules. So it's got to be pre-programmed. These are autonomous robots. Okay? So I know you can't see this. You weren't intended to. There are two programs that we're going to look at. We got two programs. This robot runs this sample A program up here. This robot program, this one runs program B that we're going to look at. So basically you have a program, you can see we have a big loop, we have a switch in the center, okay, and then we have the end, well, what I call the charge. The charge is pretty much the same. So now it's a little better. Hopefully you can see it. I think I have my laser pointing here. on this block and this block is a simple weight block. You can have these programs. Mrs. McGee will have both for both of these, okay? And you can have these slides too. So that's a simple weight block. Set the time, 5 seconds. Why? We have a mandatory 5-second delay, right? Very simple. Do that in the beginning, it's out. We go into a loop, which is the big outer square there that says, I'm going to repeat this over and over and over again, and we'll get to the end of that in a minute. As soon as we start into it, we start in with a switch, which is saying, hey, do I see a robot in front of me? Why would you want to do that? If the robot's sitting there, what would you want to do? You want to ram it. So we use a switch. Oops, back up. This one actually starts in and says 100% power, straight until I do what?
Hit a black border.
Until you hit a black border. Why would you want to stop when you hit a black border? You don't want to fall off. It's not real hard. Oops. This one's got a little more to it, because if I don't see a robot, what would I want to do? Something else, right? So what we've done here is use the math blocks. Are you familiar with the math blocks, anyone? Math blocks are fantastic. There are tons of them in the program. So what we're actually doing is using what they call a random number generator there, and we set the range between -2 and 2. The reason I'm doing that is I don't want my turn to be the same every time if I see something. It doesn't really do much good. So I have the computer select a random number, and then I decided that that number, since it was whole integers only, was too big and wasn't giving me enough variation in my terms. So I took and multiplied it by 0.5. Okay, to cut it down in size. Why wouldn't I divide it by 2? Math wizards? What happens if you divide 0? The computer goes nuts. Okay? It just doesn't like to try to divide 0. Math principles. Great way to show your kids how they actually work. Okay? And how you can get around things. So then we take and multiply it. You can add, subtract, multiply in that block. And then we apply that to our motor block. The threads. Familiar with the little threads? You can drag the thread. So what we're doing here is we're taking a random number, outputting it to this math block. We are multiplying it by 0.5. Take the answer to that and feeding it into the number of rotations our robot is making. Now I have a random turning robot. Not good for FOL probably, great for this. So then we go and we do a turn, and then we go forward until we see the black line. Again, we're just moving. This whole theory here, I had on the first slide, is, hey, if I'm moving, I'm less likely to get hit. That is one approach to a robot. I move, I look, I charge if I see something. If not, I move. That is a strategy. This is an opportunity to work on strategies and explain those to your students. At the end of this is a simple charge. And you can see these are comment blocks. You can, let's back up a little bit because I want to show you some of the things I did there. Just drag them in, you click on the upper right hand corner, puts a comment block in, you can type into it. One of the things I found very handy to do in commenting, our programmer back there will tell you, is comments are great, right?
Yeah, that one.
I put what drive motors do what, how my robot's connection. So in this program, my drive motors are B and C port. Kids always do that backwards. Every time I take them out, I'll put something wrong. This way you know. I like to use the defaults because when I pull my block in for my motor, B and C is already there. I had one team this year that reversed them for some reason. It's C and B, which you can do in these blocks. It's very easy. But every time he pulls a new block in, he has to switch the motors. What happens if you forget? Your robot does the opposite of what you tell it. Okay? You don't have to do that. If you have a reason to switch, great. Just remember you got to do it every time. The default ports, ultrasonic is 4, color sensor is 3. So I put that comment in so if anyone else is looking at my program, they know exactly what ports to plug things in, and they can double check. If the robot goes crazy, which it will do if you're plugged into the wrong port, or not do anything at all, just sit there and pull my program up and say, oh, I have my motors in A and D, no wonder why it's not moving instead of B and C. So that's an easy fix for that. Then I just tell it what it does. It stops, picks the random number, divided by half, and backs up and turns based on that random number. And then I go into my loop, which means I go back to the beginning and do this all again. Loops can be set for a number of different ways to end the loop. Right here, you click on this. I'm sure we all know what that symbol means. Right? Infinity. It'll run till the batteries die. Okay? You can set it to the number of counts. There's just a ton of selections that you can use. Here, I just want to keep on repeating this until I stop it. Because I want to keep on charging my robot until either he falls off or I do, and then we stop the match. B, strategy is to search until the opponent is found and then charge. And you will see how that works here in a second. This robot kind of sits still and is kind of pivot turn, looking for an opponent. When it finds it, it says, found them. Let's ram them and knock them off the board. So let's go on and look at that. I did this one a little different with the loop. We have the basic strategy. Please let your kids use these and start with that and encourage them to modify. Okay? These programs, this will get them started. You've been thinking, you've been explaining some things. Let them be creative. But this is a good starting point. Same thing, my ports are down here, my 5-second wait. Doing the same thing, I'm checking. But if I see something, I'm going to pass through. This is the positive check. Yes, that switch is the positive yes to that switch at the top. I'm just going to pass through because I want to go straight to my charge. Okay? If I don't, I'm going to sit here and rotate. I got my motors going opposite directions until I see something on my ultrasonic sensor. I have this one set to it's greater than or less than 12 or equal to 12 inches. You can set it in centimeters. That distance, you probably don't want it much more than 24 because it fills only 36 inches. And if someone's standing 2 feet away and you set it to 28 inches, it's going to pick them up. That's just a, easy way to work it. Oops. And if I do see something, right now I'm just spinning. I will spin continuously. I simply turn my motors on in a continual spin. So if I see something, what do I want to do? Stop. Okay. So that's my stop right there. You can see I just stop and brake. And when I do that, I'm going to do the same thing as I did in the beginning if I saw something. Charge it. The same way. After I charge, I'm going to run until I see a black line. I'm going to stop, back up a little bit. So why do we want to back up when we see a black line? Yeah, if I'm right here and I start to do a pivot turn, I guess that wasn't a good way to do it. Do it out here when you see it. If my sensor picks me up right there and I'm using a pivot turn, I lock this wheel and start turning, I'm going to fall off. So you want to back up a little bit, and then in this case I'm going to repeat my loop because that's what I'm going to do. Go back to the beginning and start looking for a robot again. So we've thrown a lot of stuff out here at you. And that's just about right. I figured about 30 minutes. I wanted to give you about 30 minutes for questions, and we'll do the demonstration, let you guys play with them, ask questions as they pop up. So these are some references. The Lego Digital Designer I mentioned is at the top. Places that you can find part numbers and parts that may not be listed on that survey that's in your packet. Obviously Lego Education US. BrickLink is excellent. I order a lot of parts from there. BrickSet, the same thing. BrickOwl has been one of the best for me. They pull parts from all over the world. And when I'm looking for parts, that's normally what I can do. But you can get the part number, you can see a picture of it, you can get what colors it's available in. That's in case they needed to do some additional research on their bomb. It's okay. Let's start him there. Let's see what he does. See how he's just sitting and spinning? Now they engaged each other. Traction, as you can see, is an issue.